Okay, so let's plug it in and see what happens. Plug it into what? I forgot. What do we plug it into? We guessed from the equation of motion. We guessed from Newton's second law. So let's plug it into Newton's second law. Okay, minus k times what? Times x. So let's write it. Minus k times a sine omega t. See, omega t instead of 2 pi over tt. That's nicer. Plus the phase. We don't know what the phase is going to be. Equals, let's see, it was minus kx equals m. And then it was d2x dt2. Sounds like a Star Wars robot, but it's not. It's the second derivative. And you say, I got to take two derivatives real fast in my head because I've had a lot of calculus. You say sine, you take the derivative of sine, it goes to cosine, and you have to multiply by the derivative of the argument with respect to time. So it turns out it's just omega. Derivative of omega t is just omega. Derivative of phi naught, a constant, is 0. So it just pulls out an omega. A omega cosine omega t. But then you do it again, and cosine becomes negative sine, and you pull out another omega. And you go back to sine. Okay, that was the calculus part. Sorry about the sleight of hand aspect of that. Okay, so it says that if you guess that this must be true, right? That's the guess. We guessed, we plugged it in. Newton says this. Newton 2 says, that's a great guess if this is true. Like you talk to the equations, right? You guess, you say, hey, Newton's law, is this right? And Newton says, yes, that is correct if this is true, right? So what is this true or not? A's cancel. The pluses, the minuses become a plus. The sine omega t plus phi naught cancels. So it's true. Newton, the ghost of Newton, says it's true if k equals m omega squared. All right? The ghost of Newton told me that. And then you say, okay, well, that doesn't mean anything. But it does, because one of those is part of the guess, and two of them are part of the system. Okay? Two of these are given to you in the problem, the spring constant and the mass. These are given. These are physical things. And this is part of the guess. So basically, when we made the guess, Newton told us what the frequency is. Omega is the square root of k over m. Newton is literally talking to you and saying, that's a good guess. It will move like that if it goes at the square root of k over m. Okay? Can this thing move at any frequency other than the square root of k over m? No. Okay? So I can give it a big amplitude. If you were to time it and get its frequency, it would be omega would be the square root of k over m. I can give it a small amplitude. And you can probably kind of tell if you just kind of snap with it. Hey, everybody. No, I hate that. Let's not do that. You can kind of tell it's basically the same period. It's the same omega. No, please stop. And it goes like that. See? Same frequency, or the same angular frequency. So omega is a property of the system. You can't change it. Okay? Now I better go back to my notes, or I'm just going to completely go crazy here.